In this magnified view of the heart, we see an autorhythmic cell adjacent to several cardiac contractile cells. Action potentials generated by autorhythmic cells create waves of depolarization that spread to contractile cells via gap junctions. If depolarization reaches threshold, the contractile cells in turn generate action potentials, first depolarizing, then repolarizing. After depolarization, the cardiac myofibrils in contractile cells slide over each other, resulting in muscle contraction. After repolarization, these cells relax. Click the autorhythmic cell to see the spread of depolarization and
Let's explore the structure of an autorhythmic cell. In this diagram, we see the structures that are crucial for generating an action potential. Embedded in the plasma membrane, we see several protein channels that allow ions to move into or out of the cell. Sodium channels and calcium channels allow sodium and calcium to enter the cell, whereas potassium channels allow potassium to leave the cell. The movement of ions affects the membrane potential, the voltage across the membrane. The membrane potential is a result of the relative concentrations of ions along the inside and outside of the plasma membrane. If there are more positive ions outside the cell, then the inside of the cell is relatively negative as shown here. If there are more positive ions inside the cell, then the inside of the cell is relatively more positive, as we will see shortly. Many transport channels are voltage-gated, that is, they open and close in response to specific voltage levels across the membrane. The gap junction connects adjacent cardiac cells. This may allow ions to pass between cells, allowing a ripple effect of initiating depolarization in one cell and then another, and so on.
Here's an overview of the initiation of action potentials in an autorhythmic cell. An autorhythmic cell has the unique ability to depolarize spontaneously, resulting in a pacemaker potential. Once threshold is reached, an action potential is initiated, which begins with further depolarization and leads to reversal of the membrane potential. Then, repolarization occurs, returning the cell to its resting membrane potential. The cell spontaneously begins to slowly depolarize once again, and the sequence is repeated. The following screens show this process in more detail. Autorhythmic cells begin depolarizing due to a slow, continuous influx of sodium and reduced efflux of potassium. Click the sodium channel to begin this slow, spontaneous depolarization process. As sodium ions enter the cell, the inner surface of the plasma membrane gradually becomes less negative, generating the pacemaker potential.
When the membrane potential gets to minus 40 millivolts, it has reached the threshold for initiating an action potential. Calcium channels open and positively charged.
Note on the graph that the calcium influx produces the rapidly rising phase of the action potential, depolarization, which results in the reversal of the membrane potential from negative to positive inside the cell. This reversal of membrane potential triggers the opening of potassium channels, resulting in potassium rapidly leaving the cell. To see the potassium efflux and the resulting repolarization, click the potassium channel. The potassium efflux produces repolarization, bringing the membrane potential back down to its resting level. Although not shown here, several other events take place during repolarization. Ionic pumps actively transport calcium back to the extracellular space, while sodium-potassium pumps transport sodium out of the cell and bring potassium into the cell, thereby restoring ion concentrations to their resting levels. Now our story moves on to the cardiac contractile cell. This cell relies on the autorhythmic cell to generate an action potential and pass the impulse down the line before the cell can contract.
Like the autorhythmic cell, it has ion transport channels, but they are slightly different.
Gap junctions link autorhythmic and contractile cells and link contractile cells with each other. Notice the sarcoplasmic reticulum, or SR, which is a storage site for calcium. Channels within the SR membrane allow calcium ions to be released into the cell. The myofilaments are the contractile units of the cardiac muscle cell. Let's look at an overview of action potential generation in contractile cells. Once threshold is reached, the action potential starts with depolarization. During the plateau period, ion movement balances out and the membrane potential doesn't change much. Then repolarization begins and the membrane potential returns to its resting state. The following screens show this process in more detail. During the depolarization in adjacent autorhythmic cells or contractile cells, a few positive ions move through the gap junctions into neighboring contractile cells. Click the gap junction to see the movement of positive ions.
This entry of positive ions brings a membrane potential to threshold, triggering voltage-gated channels, and initiates depolarization.
This voltage change stimulates the opening of voltage-regulated fast sodium channels. To see depolarization and the reversal of membrane potential, click the sodium channel.
Rapid influx of sodium results in depolarization and reversal of the membrane potential from negative inside the cell to positive. Recall that for the autorhythmic cell, it is the rapid influx of calcium and not sodium that causes depolarization. Depolarization also triggers the opening of slow calcium channels, allowing calcium to enter the cell from the extracellular space. This calcium influx triggers additional calcium release from the sarcoplasmic reticulum. Click the calcium channel to see the slow calcium influx. The slow calcium influx is briefly balanced by a declining potassium efflux, producing a plateau in the action potential tracing. Although not shown there, the calcium inside the cell initiates cell contraction.
The calcium channels close while more potassium channels open, allowing potassium to quickly leave the cell, resulting in repolarization. Click the potassium channel to begin repolarization.
The rapid potassium efflux results in repolarization, bringing the membrane potential back down to its resting level, with the interior of the plasma membrane more negative than the exterior. Although not shown here, ion pumps actively transport calcium back to the sarcoplasmic reticulum and extracellular space during repolarization, while sodium-potassium ATPases transport sodium out of the cell and bring potassium in. This pumping activity restores the ion concentrations to their resting conditions.
Click the autorhythmic cell to see the action potential wave along with corresponding graphs of action potentials in an autorhythmic cell and a contractile cell. Here's a summary of what we've covered. In autorhythmic cells, the pacemaker potential is due to the influx of sodium and reduced efflux of potassium. This triggers an action potential. Depolarization and reversal of the membrane potential is due to a rapid influx of calcium. Repolarization is due to the efflux of potassium.
For action potentials in contractile cells, the opening of voltage-gated sodium channels is triggered by the entry of positive ions from an adjacent cell. Depolarization is due to rapid influx of sodium. A plateau is produced by calcium influx, which balances the potassium efflux. Repolarization is due to the rapid efflux of potassium. To test your knowledge, click the quiz button to go to the self-quiz.